So it's our pleasure to have Katherine Stange here to give us a talk on the reciprocity obstructions and in Apollonian circle packing and continued fraction. Thank you.
All right, thank you very much. So a big thank you to the organizers for putting this together. It's been great to meet lots of people. I think my mission, as I understand it, is to keep you awake after lunch. So there'll be lots of pictures. So, all right, so this is joint work, I should mention, with James Rickards, who's a postdoc currently at CU Boulder with me, and Clyde Kurtzer and Summer Hegg, who are undergraduate and graduate students. All right. So, so I want to start by reference to what we know and love about looking at varieties and asking about their integer points or their points over a number field. And one example of such a thing might be if you have some algebraic group and you look at some particular orbit of that group. And more generally, you might ask, what if you have some subgroup, which isn't necessarily Zariski closed? And these sorts of problems come up in lots of different places. I'm going to talk about Apollonian circle packings and continued fractions, but there's all sorts of interesting connections to other places as well, other sorts of number theoretic problems that when you take a look at them end up being something about orbits like this. Okay. So before we get started with that, in the sort of classical case where you might be looking for points on a variety, we say that the Hasse principle holds if when you're looking for points over some, say, number field K, then there exist points if and only if there's points in all of the completions. And the example that you're probably familiar with is for quadratic forms by Hasse-Minkowski. A quadratic form will have some non-trivial rational solution, if only if it has non-trivial solutions in the reals and each of the p-adic fields. But sometimes the Hasse principle does not hold, in fact, perhaps more often. And a lot of the times that it fails, we can describe the failure in terms of a Brouwer-Mannon obstruction. And all I want to say about these is just that they're somehow coming from reciprocity. And so as a very simple example of such a thing, there's this famous example here, which you can show fails the Hasse principle. And the description really comes down to quadratic reciprocity. In fact, it comes down to the fact that -1 is a square mod p if and only if p is 1 mod 4. All right, so now switching gears, I want to tell you about Apollonian circle packings. Okay, so in Apollonian circle packing, you can create such a thing. Got a nice picture on my shirt here. If you start with 3 circles which are mutually tangent. And Apollonius, the reason they're called this is because Apollonius asked a bunch of geometric problems about when you have various things, can you create some new geometric object tangent or with whatever conditions? The particular question here is if I have 3 circles which are all mutually tangent, how many ways can I add another circle which is mutually tangent to the 3? So you might be able to see it in the picture. There's 2 solutions to Apollonius's problem. And so if you add those in, now you've got 5 circles and you can add more, you can ask the problem again for another triple of circles in here and add more circles in. And basically what I'm doing is just filling in all of these little sort of curvilinear triangles here with circles tangent to the 3 sides. And if you do this forever, then you get what's called an Apollonian circle packing. Okay, so this is a nice geometric object. But it turns out that in very many cases, it has a nice arithmetic quality to it. So here is an Apollonian circle packing where I've labeled each of the circles with its curvature. So the curvature is 1 over the radius. And so it ought to be surprising that everything here is an integer. They're all the radii are 1 over an integer. And this is true for the entire circle packing. The reason for this goes back to a theorem that I'll attribute to both Princess Elizabeth of Bohemia and Descartes, because they were working it out in correspondence with one another. And this says that if you have 4 mutually tangent circles, so I'll call their curvatures A, B, C, D, we'll call that a Descartes quadruple, so 4 things which are mutually tangent, sort of 3 + 1 solution of Apollonius. Then they satisfy this Descartes quadruple, the Descartes equation, okay? And so this quadratic equation reflects the fact that in the geometry, Apollonius's question has 2 solutions. If I fix A, B, C, and I ask for D, there's going to be 2 solutions to the equation. And in fact, the two solutions satisfy this nice relationship just from the quadratic equation. And this says that if I want to swap out a d for a d prime, so I'm going to get my new solution, then if my a, b, c, and d were already integers, that d prime has to be an integer as well. So what that amounts to is that if I get started with one of these packings where I have 4 circles in a Descartes quadruple configuration, all mutually tangent, with integer curvatures, then I'm going to have integers forever. Okay, so now you've got a number theory problem, right? What integers do we get? But I want to show you that this question, so here's my question. What integers do you get? What are the curvatures which appear in some integral Apollonian circle packing? I'll say primitive there because I could scale all of these things and then they'd have some common factor, but why would I do that? Okay, and so, but I want to put this in the context of an orbit. So the symmetry group which governs the fractal is the thing which lets you access the curvatures as an orbit. So the way to think about it is to think about Descartes quadruples instead of circles. So the Apollonian group is going to act on quadruples and take you around through all of the different quadruples that exist inside that packing. And the idea is that if you have, see, these red ones are like a problem of Apollonius, and these are the two solutions. I can swap out, if I have a quadruple, I can swap out one circle for the other solution to that problem. And so there's 4 ways I could do that if I start with a quadruple. And the group structure is this, if I call the swaps, the various things there. And you saw from the theorem of Elizabeth and Descartes that, in fact, the new, if I do this, if this is supposed to act on the 4 integers from my Descartes quadruple, the new curvature will be a linear combination of the previous ones, okay? And so this means that this is a matrix action. I can write it as a matrix group. So it lives inside the orthogonal group, which preserves that form, that Descartes quadratic form. It has integer entries. So it lives inside this group, say we'll say OQZ, but it's actually infinite index inside there, and yet it's Zariski dense in there. Okay, so it's not cut out by any sort of polynomial equations, which means it's actually kind of hard to tell what is in the Apollonian group. Okay, and so this, when it has these 2 properties here, it's sometimes called thin. And so this is interesting because it isn't just a Diophantine problem in the traditional sense, okay? Because we're restricting to the smaller thing. All right, now the other example of this phenomenon that I'm interested in today is continued fractions. So this is my all things continued fraction slide. So here is Carolyn Seary's way of describing what is a continued fraction. So a continued fraction is an expansion that you associate with some real number. So let's say I take a real number in here, and I'm going to associate to it some expansion, which is usually written this way. Okay, so if this is my real number, then I can write it as this continued fraction like this. But she has this beautiful geometric way of understanding it. So this is actually a picture of the Ferry fractions. So I start with 0, 1, and 1, 1. And then the mediant between those two things, adding numerator and denominator individually, gets me a half. And then the mediant between a half and 0 is a third, and so on. And you get this, this sort of recursive structure on the rational numbers. And then the continued fraction expansion can be read off as a geodesic passing through this picture. And as you enter each of these bubbles, you have to choose, am I going to the left sub-bubble or the right sub-bubble? And then I'm going to choose right and then left. And this picture can be interpreted as something about SL2Z. And so what it means in matrices, and this is what really matters to me, is that this formulation can be written this way, where my R's and L's are these matrices here. So this is right and this is left. And the number of right turns and left turns that I make, if I code them up as the exponents here, so this is like my driving directions, then if I read that off as a series of matrices, this is the exact same instructions to build a rational number as this is. Okay, so the point is that this result here is in the orbit of this vector under the group generated by these R's and L's. All right, so it's a matrix group. I'm allowing maybe some types of continued fraction expansion. So maybe I have some restrictions. If I want a subgroup of this, I could restrict to some types of words here or something like this. and I can ask about the orbit that I get, and I can ask about what rational numbers I get. So one of the sort of classical questions about continued fractions is, this is what I really should have had up when I was saying the last thing that I said. So if you just take, so I'll pause on that for 1 sec. So if you just take L and R, those matrices that I had on the last slide, they generate all of the elements of PSL2Z with positive, or sorry, non-negative entries. So this, anything in here you can kind of think of as, so think of it as a semigroup. It doesn't have inverses, but I'm going to allow multiplication. And if you think about some semigroup inside here, you can think of it as a collection of possible continued fraction expansions. And so an orbit under that is some collection of rational numbers whose continued fraction expansions come from that semigroup. So follow whatever rule it is that builds that semigroup. Okay, so this is a way of talking about sort of restrictions on the collection of continued fraction expansions. So an example might be helpful. So, so this is a conjecture of Zaremba about continued fraction expansions. Phrased in terms of continued fraction expansions, it's up top here. So what I'm going to do is I'm going to restrict myself to a finite alphabet. So normally you think of the continued fraction expansion as those numbers that are running down. And I'm just going to choose those only from a restricted alphabet. So my expansion, maybe it comes from 1 2s. So I could have 1 2 2 1 1 1 2 or whatever. It's my continued fraction expansion. If I take a look at the denominators, which appear when I'm only restricting to those coefficients, what set do I get? Okay, so what Q's have the property that there exists a P so that P over Q can be built using your alphabet? And Zaremba conjectured that if you just use 1 2 3 4 5, so you build all the rational numbers you can with expansions using only 1 2 3 4 5, then you will get every denominator. Okay, and this is open. But you can rephrase it as one of these group orbits because what you've got here is you're going to take here elements that look like this, where A is the alphabet that you're restricting to. And if you build those things inside your group, then that will get you all the continued fraction expansions of the specified type. Okay, so this can be phrased as a question about an orbit. I feel like I should probably stop and ask if there's questions. Yep. This guy? Yeah, I changed what generators I'm using. So R and L generate the entire thing. But if you take, say you take this to the 3rd power, you end up with a 3 down here. And then you take this, you end up with a 7 up there. You can rewrite that in terms of the 3, the ones that I had on the other slide with a 3 and a 7. It'll just come out the same. So I've just reorganized what I'm using as generators for the purpose of that one orbit. Yeah, but then you lose the pretty geometric picture when you do that. Or at least this particular pretty geometric picture. There's very many ways of drawing a picture of it. Other questions?
For your next slide, a conjecture. Do you know, say 6, then you know the answer is yes, something like that?
No.
Okay, all right.
No, in fact, Zaremba actually said there is a finite alphabet for which, and then he said maybe 5 works.
You know 4 doesn't work, right? That means 4.
Maybe. No, actually, there could be, yeah, there could be finitely many exceptions, but aside from those, 4 might work as far as we know, and so on all the way down to just 1 and 2. There might be finitely many exceptions. But that's quite out of reach because the data you can do, you just keep seeing exceptions and exceptions and exceptions. Who knows whether they're going to go away eventually? It's not sort of within computability when you've only got, yeah. Okay, so let's talk about what you can actually say about these orbits. So I'm going to go back to the Apollonian example. Okay, so that's -6. So the minus means that its interior includes infinity. I've inverted it. But that'll make the Descartes equation work. Yeah. Okay, and so so you can see in this picture, this one is -6. There just isn't room for a circle of curvature 2. Right? So there's a bunch of stuff that we just don't have room for. In fact, most of the stuff as we get going. But you can see that once you get up in the hundreds and the thousands, there's lots of corners to stick stuff in, right? So maybe that doesn't continue. So this is sort of a small numbers phenomenon. There's definitely some stuff missing at the beginning. And I'd say that's sort of about like how much space there is on the page. So if you want to understand what's happening a little bit further, then what you can do is you can take a look at the fractal itself and ask how many circles it's generating as it goes. So this is something just about the geometry. This doesn't have to do with the number theory, but that fractal has a Hausdorff dimension. And it's the same for any of these Apollonian circle packings. The Hausdorff dimension is. And so if you count circles, this is not counting curvatures, this is counting circles. So with multiplicity, if you happen to have repeats, the number of circles whose curvature is below a bound grows like x to the 1.3, blah, 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 that Hausdorff dimension. And so what this means in particular is that the multiplicities on average, the average multiplicity, if you have an integer Apollonian circle packing, they're going to have to be growing as well, okay? Because there's only x integers. Okay, and so, so this growth rate, there's some various results, references for that. Okay, so that says, well, maybe we should expect to see all of the integers eventually because there's lots of room for them. All right, here's a picture of the Apollonian circle packing mod 5. And the first thing you should be doing here is counting colors. There are 5 colors. So each color is one of the residue classes. Okay. Here it is mod 3. And you can see there's only 2 colors because you can only ever get 0 or 2 mod 3. You can never get anything that's 1 mod 3 in this pack. So that means that there's some sort of congruence obstruction. And so this is like a local obstruction. This is something that the prime 3 says has to happen about the packing. And then the question might be, is there sort of a local to global principle for packings like this, for orbits like this? Okay, so just for completeness, it turns out that in order to figure out what all of the congruence restrictions are, it suffices to look at mod 24. So if you have any congruence restriction that exists inside the packing, it can be phrased in terms of mod 24. Okay, so nothing more than that. And these are if you look mod 24, this is what your packing could reduce to. It could reduce to this set, this set, this set, etc. There's 6 possibilities here. And so these names here are just pretty arbitrary. This is like the number of things in the list and then the first invertible thing in the list. There's just some way of giving them names, okay? Those are the options. All right, so now we understand what the local obstructions are in some senses. So we have a complete list. Any packing is going to be one of these 6 things in the table. Okay, so where does this come from? Well, one way to think about what's going on is to think about the Cayley graph. So if you go back to the Apollonian group, it was generated by 4 swaps. And the structure of the Cayley group was that each of those swaps was an involution, so order 2, and then it was just a free product of those things. And so that means that the Cayley graph, if I use those as my generators, I can just talk about from this position, I can swap to the next element and so on. And so it's just a tree, right, growing out where it's degree 4 at every vertex. And so what I could do is to think about the orbit, I could just take say the origin of my Cayley graph and label it with the 4 quadruple, the 4 curvatures of the quadruple I'm starting with, and then just follow that out through the graph doing the swaps as indicated until you see what happens. This is a picture of doing that where you're doing it mod 8. So if I'm here with a quadruple that looks like this mod 8 and I do swap 1, I end up with another quadruple that still looks like that mod 8. And if I do swap S3, so I'm swapping out the 3rd coordinate, I change a 2 to a 6, and now I have these residues mod 8. Okay, and what you observe in this picture is, well, first of all, it's a finite graph. So it's a finite computation to do this. And in this particular example, you can see that that are missing. There's no 0, for example, there's no 1. Okay, and that means that you get a congruence restriction in the original packing if your packing reduces to this. If any quadruple in your packing reduces to this mod 8, then you're stuck in this graph mod 8, right? This is what's happening, mod 8. Okay, so that kind of explains what's going on with the where the local obstructions might be coming from. Should I ask for questions?
You mentioned about invertible in here.
Yeah, so each of the swaps, if you do it again, you get back where you started, because we're just swapping out the 1 circle and then we would go back to the original solution. Was that the question?
Yeah. I mean, you mentioned about the labeling of the first invertible element.
So that's different because this is invertible in terms of what the residues are, and that is different than the
I see.
in the group.
I see.
Yeah.
I see.
Yeah. Other questions? Okay, so let me talk a little bit more about what's happening there. One way to access this sort of computation about these local obstructions is that, in fact, you can interpret the Apollonian group. You can give a different representation of it. There's an exceptional isomorphism between these groups here. This is an orthogonal group with a signature 3-1. The Descartes form is in that category. Okay, it has signature 3-1. So we can actually move over to this group instead, and you can write your Apollonian group as a subgroup. And in fact, it turns out you can think of it as Mobius transformations, which is what this group governs, where the entries are from Gaussian integers. Okay, so PSL2 Z adjoint I. You can think of it inside there, and it's a little easier to talk about these local obstructions from that perspective. Okay, so what you can do is you can say, okay, what's happening? Say I want to classify all of the local obstructions. What's happening to this group when I dropped my P? It's gone. What's happening to this group when I reduce modulo some, say, ideal in the Gaussian integers? Okay, so this becomes finite. And it turns out that this group here, SL2, has strong approximation in the sense that well, okay, let me say something slightly different. Let me say that the Apollonian group has strong approximation in the sense that it looks like SL2 when you reduce most of the time, except for finitely often, when you reduce modulo one of these fractional ideals, you'll actually lose the fact that A was smaller. You can't see that anymore. It will just surject onto the full reduction of SL2. Okay. So what that means is that in terms of, because SL2 can move you around between all of the different residues, then A can move you around between all the different residues. So this is how you would show that you don't have a congruence obstruction at 5, for example, is because you get the full SL2 at 5. All right. This here is just explaining what happens when you look at powers. So what happens is you can, 2 and 3 are bad primes with respect to this. They don't give the full SL2. So maybe we call this bad when it's not equal. And then, but what happens is that, so something's missing. When you go, say something's missing mod 2, and you go look at mod 4, maybe more extra surprising stuff is missing. But eventually you start getting all the lifts of the stuff that you had. There's no new missing stuff, okay? And so that's why it's 24. It's an 8 and a 3. Those are the powers of 2 and 3. Okay, so that's just to give you an idea where that comes from. Now, so our motivating question is, do we get all of the integers out of this packing? Well, now we've learned that in fact we don't, because we might have some congruence obstructions. Do we get everything allowed by the congruence obstructions would be the next question. And the idea is to think about, again, these Cayley graphs, like I showed for mod 8 a moment ago, and kind of imagine that what's happening as you move around under the orbit of this Apollonian group through the quadruples of the Apollonian circle packing, you've got an image of what's happening mod P1, an image of what's happening mod P2, and so on and so forth. And in each one of those, you've got a finite Cayley graph, and it's moving around in there. And so you kind of want to understand what the behavior of that is. And it turns out that if you take a look at the spectral theory of those graphs, what they tell you is that they're very well-connected graphs. So that a random walk is going to reach all of the different vertices very quickly, okay? And so this is captured most relevantly, perhaps, in this language of like a random walk. So think of it as a Markov chain where you use your adjacency matrix to tell you from this vertex, I can walk to these adjacent vertices. And if you flow in this way, you imagine you have some mass at all of your vertices and you apply a time step and flow your mass to the adjacent vertices. That's what this is describing. Then the sort of rate at which you approach a uniform distribution of mass is controlled by the eigenvalues of this operator, okay, the adjacency matrix. And so it turns out that the collection of Cayley graphs, when you reduce modulo all of your different primes or integers, is an expander family, meaning that this gap between the first two eigenvalues, which controls the rate of mixing, is actually preserved, okay? So anyway, so this is just to give you a taste of another piece that goes into the analysis of Apollonian circle packings. And the philosophy here would be that, it's mixing up randomly modulo one prime, mixing up randomly modulo another prime. And so sort of by some kind of Chinese remainder theorem, if these are kind of independent, then you would expect that in the global situation, as you move around through the Apollonian circle packing, you're going to be getting all integers. All right. So maybe if each of these is mixing well and hitting all of the residue classes, do you get all the combinations of residue class? You get all of your integers. Okay. That's very hand wavy and big. Okay. So, all right. So what are the sorts of obstructions? So this is to sum up a little bit of what we saw. So we have, in this case, it's definiteness in the sense that it's finite in one direction. Like in the Apollonian circle packing, there's only at most one negative curvature, that outer one. Okay. We saw that the growth rate, that Hausdorff dimension, governed how many circles you're getting. That needs to be big enough for you to expect to get lots of integers. So this growth rate, sometimes when we talk about thin orbits, we're talking about the growth rate being smaller than sort of the ambient algebraic group. So you need that to allow, this was supposed to be TOO here. You need that to allow for increasing average multiplicity. Then we saw there are congruence obstructions. Your orbit might not intersect some particular congruence class. And remember that this is an orbit of a group which lives inside some algebraic group, and that algebraic group itself might have some type of obstruction on its orbits, in which case you would inherit that. Okay, so these are the sorts of things that we know of. So the conjecture then, which is originally due to Graham, Ligarius, Malles, Wilkes, and Jan, so they wrote a series of papers in the 2000s on this topic, and then refined a little bit by Fuchs and Sandin, who collected some data later, is that, yeah, you would get everything that isn't already ruled out. So in a primitive integral Apollonian circle packing, the curvatures will satisfy a congruence condition mod 24, and all sufficiently large integers that satisfy that condition will appear. So finitely many things missing at the beginning, some congruence classes missing, everything else should appear. You can think of this as a growth statement, which is that if I count the number of curvatures appearing up to size n, it should grow as a constant multiple of n, where n is just the ratio of the number of admissible classes mod 24 out of all classes, and then plus just a finite error term. All right. And so one might study this function. It's sort of a representation function or something like that. Okay, so the history of this function. So the first bullet here is just the growth of the curvatures themselves. But now for k of n, Graham, Ligarius, Malles, Wilkes, and Jan in their original paper gave a lower bound of root n. And then Sarnak took an interest in this and wrote a letter to Ligarius in which he explains, using some relations with quadratic forms, an improved lower bound. And then Bourgain and Fuchs were able to show positive density, meaning some constant multiple of n as a lower bound, but not necessarily the 6 or 8 over 24 that we're looking for. And then Bourgain and Kantorovich were able to get the correct constant multiple of n with a power savings, which means density 1 within the admissible curvatures. Okay, questions? The k has to be the 6 or 8 over 24 for the number of residue classes. Yeah, it is the correct thing. Yeah, and then I put this on because it has my name in it. We did a generalization to some other classes of packings as well. Okay, so one of the tools that gets used is this nice observation. This is important for later in the talk, that there is a bijection between the family of curvatures, which is tangent to some fixed circle I'm going to pick. Okay, so if I look at 11, then it's this blue family, all the stuff tangent to 11. Those are exactly, those numbers are just those represented by a particular binary quadratic form, translated by 11, translated by that curvature. Okay, the things that are primitively represented. And that form here, this guy here associated with the circle C, it has discriminant -4a squared, where a is my curvature. Okay, so you can write this down explicitly, and that means that the collection of circles in the packing may be very mysterious, but it's made up out of pieces that we understand fairly well, right? They're values of quadratic forms. And so Bourgain and Fuchs, what they did, they used some sieve methods, circle method, and at the very highest level, what they did was they collected sort of an ensemble of such quadratic forms and collected together all of the values, counted those up, and then, you know, an inclusion-exclusion argument here, they have to account for whatever double counting could occur. So bounding these two can eventually get you their result. Bourgain and Kantarovich. Again, it's the same sort of argument. What you've got is kind of, here the notation is different, but this is a collection of quadratic forms again. I've just, for some reason, labeled it by gamma, okay? That's the matrix. You're going to take a collection, and then you're going to take a range of inputs, and you're going to count this, the characteristic function for getting out the number you're interested in. So this is how many times n is represented in the circle packing. And then you're going to let these things grow very carefully in tandem with one another to try to count using circle method to show that this is positive. Okay. So those are where the analytic results come from, but I'm not I'm not going to talk too much about the analytic results because I don't really think of myself as an analytic number theorist. I hang out with analytic number theorists sometimes. But you know, it's dangerous, right? That joke about what's the sound of an analytic number theorist drowning? You know this joke, right? Log, 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 log. So they're dangerous. All right, so let's go to computational evidence. So Fuchs and Sandin computed for these two packings. These are like the initial quadruples. And this guy here, they called the bug eye because they were just having fun. They drew this picture here. This is from their paper. And what they did to figure out, okay, remember we saw that the average multiplicity has to be growing. So what they did is they took a histogram of the multiplicities. So if you look at a range of curvatures, so your curvatures start over here and they keep going, and you pick a little range. And then within that range, you count the multiplicities. So maybe I had multiplicity 10, 15 times, right? So these are the multiplicities down here, and this is a histogram of how often I hit those multiplicities in that range. So for this range here, this one like 10 to the 6 to 10 to the 8, and I've restricted to a congruence class, then I see that the average is somewhere around here, right? So I'm getting about 400 times each number in that range. And I don't seem to be getting anything down here. And then as this range increases, I take farther and farther out ranges, this wave will move off to the right, okay? So this was how they collected and looked at the data as evidence that you're not getting anything of multiplicity 0, because that's stuff that's actually honestly missing, right? So what you're trying to show is that everything is kind of going out the same and not leaving anything back at 0. All right, so let's call a curvature missing if it is allowed mod 24, but it doesn't actually show up in the packing. So they went up to this far, and for this guy, there were still just a few missing curvatures in that range for just a few of the residue classes. All right, so they didn't get far enough to not see the missing, to see the missing curvatures go away. Okay, and so this brings me to the summer RU from this summer. And so this was myself and my postdoc, James Rickards. We were running an RU with a couple of students. And based on something James had done before, which was quite interesting, which turns the question around, instead of asking, here's a packing, what are the curvatures? It asks, here's a curvature, what packings contain it and how deep does it lie? So we asked the students, okay, here's a pair of curvatures. What packings can contain them both at the same time? So that was the question. And the first thing to do is collect data. So for a pair of, we broke it up by the residue classes mod 24. So pick 2 residue classes mod 24, which are allowed to go together. And then graph all of the curvatures from one residue class versus all the curvatures from the other one, and just put a dot if they occur together in some packing, and leave it blank if they don't. Okay, so this should just be, or sorry, it's the other way around. Leave a dot, I've got it written up here. Black dot if no packing has that pair. So that's where they don't occur together, and leave it blank if they do somewhere. Because it's kind of, what's interesting is the times when they don't occur together, okay? All right, so if the local global conjecture is true, then if I fix a row or a column, that's fixing one thing and asking what other curvatures can occur with it. And I've picked a residue class that's allowed, so it's not a congruence restriction here. So I should only see finitely many dots in any row or column, all right? And so these are the actual graphs, not made for distribution, but just for like us to look at. And so here's, so yeah, so I mean, I don't know why all of things are arranged this way, right? But the X and the Y coordinates, the origin is way up here. And you see just a scattering of black dots, which eventually peter out as X and Y get large. Okay, and here's a zoom up, and they look different shapes just because of the sampling of the graphic. All right, so yeah, so this is kind of what we were expecting, and we were going to ask questions about like how far do they peter out, or if there's some favoritism of some kind, or any trends, anything that we saw. Really, we were just playing around. Okay, and so there's lots of different pairs of residue classes to compare, and so Summer set the computer up to create all of them. There are like 100 of these different graphs, and they all look like this except for one graph, and this one had these very regular lines. And if these lines don't peter out, that means the local global conjecture is false. And so there's no like missing dots on any of these. There's extra dots, right? There's some noise at the beginning, but there's no indication that they're going to go away. So the first thing that we thought is, okay, there's probably some very strange computing error here, some bug in the code or whatever. So we looked for that for a while. And then we said, well, what if it's actually false? Okay, now here's a different story. This is the imaginary story in which we discovered it a different way. But I like the graphic. So in this picture, imagine we had done this and it would be kind of a cool thing to do. This is for one of these packings. This is the first 4,000 curvatures. And what I've done is I've graphed the difference between one curvature and the next. It's like the gap, okay? And the curvatures these are the missing curvatures. So they start to spread out and peter out and seem to look like they're going to disappear. And so what you see is that the differences between them are gradually growing, but it sure looks noisy, like it's not a pattern, right? So this is up to the first 4,000 curvatures. And in fact, if you keep going, and I'm just going to zoom the same graph out, you see what happened to the slide. It actually continued right up to 10,000 last time I looked at it. PDF did something weird. It's good enough. This is where we were looking before. This is where we stopped before. And you can see that they become very regular. And so the noisy stuff, the really honest to goodness, randomly missing stuff, has stopped by around here mostly. And what's left is clearly a family of some kind. And if you think about it, having a pattern when you're looking at successive differences is something you'd expect from quadratic growth. There's several different quadratic families hiding in here, in fact, and that's why you get this sort of interference pattern. Will it like get bigger if I do this? That's so weird. Truly strange. Something to do with the compiling. Okay, so the conjecture is false. And here's just an example theorem explaining why it's false. So an Apollonian circle packing, if I take this particular one generated by -3588, then its peculiarity is it never has a square curvature. So that's a whole quadratic family that's missing. And I can give you the proof for this one because all of the complicated details distill out in this one example. So we classified it for all of the possible Apollonian circle packings, but it's easier to understand in this one here. So here's the proof. I'm still allowed to talk, right? Okay. So fix a circle of curvature n. And remember that we have this quadratic family of stuff touching it. So all of the curvatures tangent to it are things that look like this, from this quadratic form here of discriminant -4n squared and then -n on all of those numbers. Okay. Now, if I look at that mod n, what happens? Well, the discriminant becomes 0. This becomes a degenerate form. So if I change variables, it looks like this. And this a is a constant, which is either a residue or a non-residue, right? So particularly, like, let's think of n as being prime for this argument here. Then this has got quadratic residues or quadratic non-residues, but doesn't mix them up, okay? So what that means is this Kronecker symbol, I'm saying Kronecker symbol so that I can allow n not to be prime. This has to take, it can't take both values 1 and -1. It might have some zeros, right? But it can't take 1 and -1. So we can give it a name. We can say the chi2 of that circle is 1 or -1, whichever thing is happening, okay? And to compute that, it's just the Kronecker symbol of some curvature coprime to n and tangent to n, and that's will allow me to compute it. So it's easy to check for any given circle. Questions? All right, so this is just about the one quadratic form. Yeah. No worries. These ones? These ones. So what's happening is I'm just comparing, I'm going to start with a pair and ask if there's a packing that contains both. So the x-axis is a selection of possible curvatures. And the y-axis is a selection of possible curvatures. What's actually written here is like, it's this number times 24 plus the residue class I'm interested in, to get, they're spaced out by 24, and that's not shown. Like, these were the original data, right? So we didn't make it nice to read. But anyway, this is a list of actual curvatures that all have the same residue mod 24. And then this is also. And then I put a dot if there's no packing in which they occur together, so they repel each other. And then I leave it blank if they can occur together somewhere. Different residue classes, so this differs for different ones. Good? Other questions? All right, awesome. So what we've got right now is that if you're standing at one circle in the Apollonian circle packing and you look around, you can't say too much about what you see, but if you look mod your own curvature, then you can see only residues or non-residues, or at least if you're not prime, you should say you can see only things of chronic or symbol 1 or -1, but not both. Okay? All right, so now that's just from one position. But if you have two circles which are tangent and they have coprime curvatures A and B, then I could use, if you've got these two circles, I can use this circle to compute the chi2 of this circle, and I can use this circle to compute the chi2 of that circle, right? Because you just need to look at a neighbor to check what your chi is. So quadratic reciprocity says, if I multiply the chi2 of the first circle by the second one, I'm actually just checking A mod B and B mod A. And in this particular packing, there's nothing that's 3 mod 4. It's all 1 mod 4 by the mod 24 restrictions. And so by quadratic reciprocity, this comes out to 1. And so in this particular packing, those two things have to be the same. So I've taken one step in the packing and my chi2 has not changed. So the argument finishes off by saying any two circles are connected by a path of coprime curvatures. And then this chi, you can think of chi2 being -1 as ruling out squares modulo your curvature. That happens throughout the entire packing. So there can't be a square anywhere in the entire packing. All right, and so we just have to check that this packing that we've got is a -1. So we just do one computation of one tangent pair. All right, and so then there's no squares in there. And so what's kind of cool about this is that now we have these invariants of the packing. They're not just invariants of the circle, but invariants of the whole packing. And they're somehow tied to residuosity, and they create these obstructions. So it's reminiscent of like a Brouwer-Mann obstruction. It turns out that there's also quartic reciprocity happening because there's something about the Gaussian integers. Remember, we could put it in Mobius transformations PSL2 zeta join I. So there's also a quartic phenomenon that happens sometimes. And so then we can classify everything. All right, it's probably not worth going into the details of this, but these are the missing families depending on what type of packing you're in. Yeah. We were just calling it a reciprocity obstruction because it was either quadratic or quartic. At first, we weren't sure whether we would see anything else, but they're all coming from these symbols. So it's either the quartic residue symbol or the quadratic. Good question. Edna might be your woman. I don't know. Yeah. So with the remaining time of which I don't know how much longer am I supposed to talk? 15 minutes I'm allowed. Okay. I was going to say, and I will, since I'm still allowed to talk, something about continued fractions. So that's another situation in which we see something like this. Because that's the question now, is like, how general a phenomenon is this, right? So this is an interesting example, but the question is, for thin orbits in general, what are the possible behaviors of these things? Okay, so let's call the things that are missing, but missing without leave. So missing even though they're allowed by the congruence obstruction and they're allowed by these reciprocity obstructions. Let's call those sporadic. Okay, so definitely, like, at the beginning, there's a bunch of sporadic stuff because, like we saw, there isn't room for everything. Then the new conjecture is that that's finite. So you take out the congruence obstruction, and then you take out these quadratic or quartic families that are listed in that previous table. And then the new conjecture is that there should be only finitely many things missing. Yeah, and I think this is just as hard as it was before. It's funny because when I saw Sarnak, I said, I hinted that we had figured out something about the Apollonian local to global conjecture, and he said, oh, you've proven it's false, because there's no way, nobody knows how to prove it, it's true. So there is some computational evidence. So James is absolutely amazing at efficient computation, and he writes in C, so it's nice and fast. And we were able to go up to about 10 to the 12, curvatures of size 10 to the 12, and compute these sporadic sets. And what we did is in each of those sort of categories, those types that you saw in the big table, we picked 3 smallest looking packings, and we went until we saw the sporadic set appear to stop. So we went till we were like some multiple of the last one and hadn't seen another one. I think multiple is like 10 or something like that. And so that's some evidence, perhaps, that we've got it right. I don't know. Okay, so this sort of adds a new type of way that these orbits can be controlled. All right. All right, so what about the Zaremba conjecture? So, okay, so again, just like in the Apollonian case, you have to say something about growth. So you have to know that you're getting enough stuff in your orbit that you have a hope of hitting all of the integers, say, as denominators. Okay, so what this amounts to in this situation is that if you have some semigroup inside SL2Z with non-negative entries, then you can think of this as a continued fraction semigroup, and it has some limit set in the real line. And so you can ask about the Hausdorff dimension of that limit set, and that's the analog of the Hausdorff dimension of the Apollonian packing. And depending on the alphabet that you're using, say we were talking about for Zaremba 1, 2, 3, 4, 5, you get different Hausdorff dimensions. And if the Hausdorff, there's a result due to Hensley that says that if your Hausdorff dimension is delta A, then you can expect the number of denominators below a certain bound that you're seeing in your orbit to be this many. It doesn't say anything about, you know, which ones you get, just the total number of sort of rational numbers you're getting whose denominators are below that. Okay, and so it's a growth depending on the Hausdorff dimension, and if you're bigger than a half, then you expect average multiplicity to go to infinity, and you have some hope. So Hensley said that if this is bigger than a half, so his conjecture was then, okay, you should get all but finitely many positive integers. So this is like a local global conjecture. Here are the different alphabets that you might look at and their Hausdorff dimensions. They're all bigger than a half. So even 1, 2, Hensley says, should contain all but finitely many positive integers. Bourgain and Kantorovich looked at this set, which is all evens, and they noticed that the alphabet, that if you use these to generate, then your denominators miss 3 mod 4. So they found a congruence obstruction. So that means that Hensley's conjecture, as stated, is wrong. It should say there's some congruence obstructions, and then maybe finitely many. Okay. And so the question is, in a situation like this, do you expect to see some reciprocity obstructions also? Any questions? All right. So we have a lot of planted questions in this audience, this whole conference. Yeah, so sub-semigroups. All right, we think of these as having some sort of restricted continued fraction expansion. So James and I, this part is joint with James Rickards, that we were looking to see if we could find something like this here. And so we were looking around inside the world of possible semigroups inside SL2Z non-negative entries. And this subset is quite interesting because remember, it's something to do with reciprocity. We're working in integers, so like quadratic reciprocity is the best target. So take the collection of matrices where the Kronecker symbol between 2 of the entries is 1. This is kind of a weird thing to do, maybe, but maybe not in context. We found it was useful to restrict to gamma 1, 4 because, like you saw before, everything's easier if you don't have 3 mod 4 things. Okay, so this was why the 4. So gamma 1, 4 is just that congruent subgroup, but inside this. Okay, so we called this psi, and what we showed first is that this is actually a sub-semigroup, which is in itself kind of fascinating. Why should it be that when I multiply 2 things that have this Kronecker symbol in terms of their entries, you'd still get something that has that property? And it turns out that if you think about this as what it's, you can ask, what is this saying about continued fractions? It's actually saying, like, think about a continued fraction P over Q. Say it's Kronecker positive if P over Q as Kronecker symbol is 1. This says that the property of being Kronecker positive is preserved when you concatenate continued fraction expansions. There's an asterisk here. You can look up the actual statement, but it's basically this, is that the continued fraction expansion, if it gives you something with positive Kronecker symbol, and then you just tack on, like literally concatenate the continued fraction expansions of two things of that type, then you'll get another thing of that type. Which I haven't seen anywhere, and I'm really curious if anybody has seen something like this to know of the references, if there are. It seems like a fascinating statement, but yeah. So what we're able to show is that when you use this, you do get these reciprocity obstructions. So I'm going to take an orbit of this thing, which is a sub-semigroup. If I'm an orbit of xy where xy starts with negative Kronecker symbol, then both the numerators and denominators of anything in that orbit can never be a square. And this is sort of the simplest example of such a thing. It comes from quadratic reciprocity again. It's much more contrived and constructed. You can see that, like, we made this to do this. But it's sort of surprising that it worked out when we tried to do that, actually. And the other thing you might object is that this isn't really like the Zaremba things, right? I mean, it is sub-semigroup, but it's sort of a weird sub-semigroup. It's the collection of things whose continued fraction expansions. I mean, it's a sub-semigroup. You concatenate them, you get another thing of that type, but it's the collection of sort of Kronecker positive rational numbers. But if you want to build something more along those lines, you can pull out smaller sub-semigroups. So here's one where the Hausdorff dimension here, I think maybe I forgot to divide by a half on this one. And this is just generated by these two things. This plus means I'm generating as a semigroup, so I'm not including inverses necessarily. And those are two very simple matrices that look like continued fraction kinds of matrices. And these have congruence obstructions mod 4, sorry. But if you put in 2, 3, then you will not see any congruence obstructions in that orbit, but you will not see squares in the numerators in this case. Okay. And in fact, we computed data up to 10 to the 7, and we think the last sort of sporadic thing that's actually missing is just this size, and everything else except for squares will appear. So this is an example of that type. And you can rephrase this example in terms of continued fractions to make it seem more like a Zaremba type example. So if we take the rational numbers whose continued fraction expansions look like this is my alphabet. It's the multiples of 4 between 4 and 128. And then I tack on 112 at the end. Then all of those rational numbers, it has an associated Hausdorff dimension that's bigger than a half, so like seems reasonable. But there's no congruence obstructions, but no squares. And this disproves the conjecture of Bourgain and Kontorovich about such things. They also studied Zaremba's conjecture and proved, I think, I forgot to say some of the results, density 1 and stuff like that. And I should stop there and ask for questions. Thank you.
Okay, for the wonderful talk. Any questions?
What exactly was the conjecture by Bourgain and Kontorovich that was pretty good?
Right. Yeah. So they it's funny because it's stated in a paper by Kontorovich, which is sort of an expository notes, and it says something like, you know, finite alphabet, infinite orbit, Hausdorff dimension bigger than a half, then you should have a local to global. But he told me when talking about it that they meant, you know, from sort of any orbit, which means there's sort of two slight generalizations to what that says, right? And the caveat is this little bit right here, right? It doesn't seem like it's quite a Zaremba type thing. You can change this by saying, if you're saying in terms of a group orbit, you change the thing you're taking the orbit of to be 2, 3 instead of 1, 0. And that accounts for this little thing. This is the continued fraction expansion of like 2/3 or whatever. And so he said that that's the generality in which it was meant. So disproves the conjecture of Bourgain and Kontorovich. That's like according to Kontorovich, it does. No, it's in some notes from a summer school, I think.
Any
It's
other,
cited in our paper, so, which is on archive, so I can find it for you.
any other questions? Okay, if no, then we will go out for the afternoon tea. May I propose the last talk starts 5 minutes later than the schedule so that we all have enough time to use the bathroom if necessary. All right, so the last talk will start 5 minutes later than
Are
the
you talking
schedule.
about the talk
The last
after this
talk,
break?
the last talk, last plenary talk.
Oh, okay.
The separated session will be on schedule. The last talk of today, 4:30, Winnie Lee's talk will start at 4:35 instead of 4:30, so that we all have enough time to go to the bathroom. All right, okay. Thank you, Kay, again for the wonderful talk.